Maddie. We are the Laser Weed Management Team sponsored by the Department of AgriLife and the School of Innovation.
My name is Joshua Anderson, and I'm a computer engineer.
My name is Cameron Armand, and I'm an electrical engineer.
My name is Abigail Doherty, and I'm a computer engineering major.
And my name is Michael Go, and I'm an electrical engineering major.
Okay, so this is the diagram of the main system. There are four main subsystems. I'm in charge of the power subsystem. The power subsystem is responsible for supplying power to the three main electrical components: the Micro Maestro 6-channel servo controller, the laser, and the NVIDIA Jetson. Josh is in charge of the image processing subsystem. This subsystem captures images of the weeds with the Intel RealSense D435, processes them with machine learning to identify the weeds, and then finally outputs the location of the weeds to the motor system. Cameron is in charge of the motor and hardware subsystem. This subsystem takes the locations provided by the image processing subsystem and converts them into motor movements. This subsystem also includes the designing of additional hardware for our system. Abigail is in charge of the laser subsystem. This subsystem includes research to verify the most effective method of killing the weeds and the logic for aiming and firing the lasers.
I trained the faster RCNN model using various data sets, both from open source and created ourselves. I coded the camera control system, and I coded the object detection algorithm that passes data from the Python faster RCNN model to the object detection class, and then passes the data to the motor control. And last, I created the Python code that runs the faster RCNN model and calculates the stem location. So this is the image processing flowchart. First thing I do is capture an image and then save it to the directory, and then I execute the machine learning model, and I return a XY pixel location. I get the depth image from the depth camera based on the pixel location given by the Python script, and then I check if the weed is present, and if it is, I pass it via the FIFO pipe, and then I go back to capturing an image. For the FIFO piping mechanism, the motor control creates a thread, handle pipe, and it waits for reading, and then the object detection aspect of the pipe executes the Python code, and then in the object detection side, it gets the variables and then it writes it to the pipe. So for the camera class, basically it does two things. It takes a picture and it calculates the depth. And the video frame is saved whenever I take, which is the depth frame, it saves whenever I take a picture. And here's the CPP for that. For the Python script that runs the faster RCNN model, it grabs the images and then it executes, and then I grab the coordinates and I calculate the coordinates of the bounding box, and then I calculate where the stem would be. I have three main iterations for training. The first one is a one-class model that is created from approximately 100 pictures taken from home of the weeds I have on hand. This has a greater than 90% accuracy. The second iteration is of the Pascal VOC 2012 dataset. This needs more training time on a stronger GPU. However, this dataset is more accurate than third. I started training this dataset because I was worried about the third dataset's accuracy. This was created to verify the functionality of the machine learning. The third iteration is of the DeepWeeds dataset. Although it is functional, the accuracy is not quite as sufficient. This could be improved in later months with sufficient training on a strong GPU.
Okay, now I'm going to go over the motor control and hardware subsystem. So the things that we have to deliver are the hardware, actually mounting everything physically, interfacing all of the components we have together, and then converting pixels to inches in physical space, and then converting those physical locations into actual motor movements. Before we left before spring break, luckily we were able to get everything mounted on top of the frame. Pretty much the last thing we need to do is we need to 3D print this little model here, and that's how we're going to mount the camera to the frame. We figured out where we want to have the camera and which way we want it oriented, so that'll be the last thing we need to do physically. So here's just kind of a general breakdown of how the system works. We receive a pixel location from the image processing of where our weed is. So we convert those pixels into inches. And then from that, we find the necessary angle we need to move the gimbal system. We convert that into a coordinate system that the motor can recognize. And then this servo controller, which outputs pulse width modulation, controls the laser as well as the actual gimbal. So the laser takes pulse width modulation to turn on and off. So this controller will tell the gimbal where it needs to go, and then turn the laser on, and then move the laser across the weed, and then turn the laser off.
All right, now we're going to do a demo of the motor code. So this is kind of a general output of, what we're looking to get out of it. We're going to get a pixel input, which we're going to convert into inches under the frame. And then this will output degrees, which we can send to the gimbal to move to those degree values, and then hit the target we're trying to hit. If you look at the code, the first thing it does is if you look here, we're gonna see these X image, and we're gonna get pixel values, X and Y from the camera, and we're gonna get a Z value in millimeters, how far away the weed is from the top of the frame. And then those will be converted with simple multiplication into inches. And we chose to do this way because we figured it'd be way easier to verify. If we have physical inches locations under it, it'll be easier to measure and see if we're going to the right place. And then you can see there's some dummy values in there. There's a few more in the code, but we've defined all these on the top. And as soon as the semester starts again in the fall, we'll go and measure these values, and then hypothetically we'll be able to hit any location that we measure out on the ground under the frame.
For a brief overview of this system, we essentially have two main classes. We have the weed class, which is essentially the objects of weeds that have the coordinate system and the value of whether or not the weeds have been killed. And then also we have the motor track class, which stores weeds and also converts the coordinates and sends actual moves to the motor system. A few notable things to look at here is these functions here, the left-right motor calc and the theta to motor functions. These are the functions that are actually performing the calculations to get the degrees that are required to get to the weed. Some other functions that are notable is this move laser function, which converts those degrees into actual steps for the servo motor. Additionally, this function here, kill weed, is what sets the laser to on or off. The laser is also using the MicroMaestro device, except the laser channel is set to an output, so it has a 1 or a 0, and this system uses, if it's greater than 6,000, it reads as a 1. So that's what this function is doing here. It's just killing the weed. And then finally, one thing that's important to note is this set target function. This function is something that we have found online that is controlling the MicroMaestro device. Luckily, before spring break, we were able to implement this function and verify that it does in fact work with the MicroMaestro, and we were able to get it moving the motors. However, we don't have access to that hardware right now, and so as we call set target, it's essentially outputting what it would be doing if it was connected to the hardware. I'm going to do a quick demonstration of the motor code. So if I hit test, if I run it, it outputs the values as it goes through. So it has received an image coordinate, and this value here is in meters, and then it converts it to inches, and then returns the new coordinate in inches. And then it reports the weed status, which is alive because the lasers have not fired yet. And then here you can see that the angles have been calculated, which match the image to the right on the PowerPoint slide. You can see 58 degrees and 88 degrees, just to help visualize. And then after the degrees are calculated, we move the servos to those locations, and then the laser is turned on. And then next, we're moving the servos back and forth. It iterates a few times across the stem of the weed, 1 degree to the left and right. And then after it has fired the laser is turned off, and the new weed status reported, which is killed. For the laser research and tracking subsystem, my main deliverables are a plan working on the future plant research that will be conducted in the fall, and then code for both types of laser testing that I will be performing, and then also code for dynamic tracking. For the laser research plans, there are 2 main types of tests that I will be conducting in the fall. The first is tests that will fire the laser for 1 or 2 seconds at a fixed point at the stem of a weed. And then the second testing will include 1 and 2 second tests of firing at the weed and moving across the stem to the left and right. These tests are important to verify the ability of the laser to kill the weeds. The accuracy of the motor and the laser will help to determine the required speed of the system. For example, if the weeds require 2 seconds of firing to effectively be killed, the system cannot be moving so fast such that the weed would move out of the frame before it has died. This is a flowchart for the different types of tests that have been created for the laser testing. So essentially, the 2 different tests will move the motors to the weed location, turn the laser on, and then there are 2 different tests that will be performed. If you look to the code on the left, I'm going to run a quick application example of the testing. So using these variables here, we'll have demo 1, and we'll first run a static test. So in the static test, it converts the coordinates, finds the proper angles, and then the servos move to the location of the weed. And then the laser is turned on, it sleeps for 1 second, and then the laser is turned back off. And then if we run the laser again with the same location, and this time we run the dynamic test, you can see it still moves to the same servo location, but then after the laser is turned on, the servo moves back and forth, left and right, 1 degree across the location, across the stem of the weed. And then after it has iterated a few times across the stem, the laser turns off. Prior to spring break, we were able to connect the MicroMaestro to the servo controllers. We had begun initial testing to calibrate them. In the video, the MicroMaestro had been coded to move to specific points in a loop using a laser pointer for testing.
Okay, so this is the demo for the power subsystem. I'll be showing the 6-volt buck converter that will be used to power the MicroMaestro, which in turn powers our motor system. So for the power system, I'll be demoing the 6-volt buck converter design. The converter will be used to step down the voltage coming out from our 12-volt battery to an appropriate level for the MicroMaestro controller, which powers the motor system. I'll be going over the simulations for the converter, including the line and load regulation tests, and then showing my PCB layout, including the schematic, DRC tests, Gerber and drill files, and lastly, the bill of materials. So I used WeBench to test the line and load regulation. Here I put the converter through an input transient simulation, which varies the input voltage from 10 to 12 volts. As you can see, the output voltage varies as the input voltage varies, but the change is only between 5.97 and 5.935 volts, which is pretty good as it's near the 6-volt goal that we have. Calculating a line regulation percentage, I got 1.75%, which is pretty good for the system. For the load regulation test, I ran a load transient simulation, and as you can see, the output current, which is like the load of the converter, varies from 5 to 0.5 amps. The output voltage does vary a bit as a result, going a bit over 6 volts and at 5.9 volts when the current dips and rises, but overall stays consistent and steady at around 5.94 to 6 volts. Calculating the load percentage, we get about 3.11%, which is pretty acceptable given that. The schematic for the converter, it is very similar to the schematic that was printed out by WeBench. The only changes is that I added the wire to terminal blocks here and here to connect the PCB easier to wire to the battery and controller. So this is the PCB layout and the 3D model. I ran the design rule check, which is 0 warnings, 0 violations, and I successfully generate the Gerber and drill files. Let me just show you the files here, which I will be running. Here's a 3D model of the converter, the back if you want to see it. I'll just run the design rule check. As you can see, 0 warnings, 0 violations, all good. Now I'll fabricate the Gerber and the drill files. So to verify these Gerber and drill files, I'll pull up a third-party viewer, just to check if the Gerber files and the drill files are good to go. So as you can see, these are all the Gerber files that are needed for the PCB manufacturer. I can go through it layer by layer. The bottom layer, bottom paste, bottom solder, top layer, top paste. It's all good. And now for the drill files. Let me get that. You can see the drill files are all here and good. Tells you where the manufacturer has to drill the holes at. And so yeah. Back to the presentation. Now I have made the bill of materials. I have all the information on all the components in the budget list. All I have to do is send them up for approval to you guys. And then after that's approved, I'll have to choose a PCB manufacturer. Here are some of the PCB manufacturers I found online, but I would rather get a recommendation from you guys about which PCB manufacturer to use. Yeah, that's about it.
Yeah, this is the full system integrated together. It takes a picture, and then this is the motor control, and this is the output of the machine learning. And this is the piping. With the system fully integrated, we'll be able to implement it on hardware coming in the fall.